Hey everybody, so let's continue this thread and now let's learn how to fill polygons in general. So if there's one thing you can learn that'll give you all the answers you need about, there's one thing you can learn that'll give you all the answers you need about polygons, and filling them is don't bother. It's too much work. Turn them into triangles instead. Don't fill. And we learned that in a previous class. Turn them into triangles. Okay? And then you're done. If we have triangles, we know how to work with them. Problem solved. Alright, next unit. No, unfortunately, we'll still go through how to fill polygons. Although it's not very fun. So I'm going to draw this polygon, and I'm going to see if I can get it right. And put arrows in here, because polygons do have winding. Okay, this way, this way, this way, this way. Okay, I hope I got this right. And all these lines are perfectly straight. Let's try fixing that. There we go. Okay, so the winding is this way, this way, this way, this way, this way, this way. I'm running a circle. This is a kind of polygon, and this is an example that was cooked up to show some of the complexities. And we can go through some examples here of what the heck we do with all these. First of all, we still do the scanline approach. That's great. You can get your bounding box the same way. Get your bounding box, go through the y's, go through the x's. Cool. But our previous test that we used to see if a point is inside a triangle isn't going to work here. There's too many points. So instead what we do is we cast a line segment. We just do it, we don't actually draw a line, right? We just pretend we do. We cast a line segment from our point. Let's see, I'm going to have a point here. So we cast a line segment from each point. I'm getting tired of this. Okay. From each point. Okay, so we cast a line segment from each point that we go across. Like in the triangle one, we tested each point if it's inside the triangle. We do the same here. We go through each point, and from that, we cast a line segment to the edge of the bounding box. Okay, so bam, just like that. Cast a line segment out. And then, we can do it all over the place. There's a point here. We do, not only can we do it all over the place, we do it all over the place. But I'm just drawing these because these are some examples that I'll work through. Yep, so we still do these scan lines, scan, 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 and at each point, we draw the line and we cast it out. Cool, so when we figure out what that line is, now what we do is something new. We calculate line intersections between your casted line and every line in the polygon, okay? So for this line here, I go, okay, I figured out it's from this point to that point. Cool. You parameterize it, and then you go through every one of these green lines and you do the line intersection formula that we discussed in a previous class, and you find out if they intersect. So you do that for every combination of lines. You go through each point and you intersect it with every other line. Okay, let's see. Now, when you do that, there are two rules we can follow. One is called the even odd parity rule. Okay, even odd parity rule. And what the even odd parity rule does is we just count. You know, this is so stupid. It jumps when the taskbar comes up, and then it messes with my writing. What if I was an artist? And like my sketch was, I came up with a perfect curve, and then they screwed it up just that one time. So we count the number of crossings. Okay, we count these crossings. So if I take my pen here, this line I pointed to, there's 1, 2 crossings, okay? 1, 2, 3 crossings. This one has 1, 2 crossings. So we count the number of crossings. And what we do is we go, oh, if it's even, the point is outside. Easy. If it's even, the point's outside because we went in, we came out. We went in, we came out. Right? The only way that can happen. If our point starts inside, we can't go out and go in again. We need to finish by going out. So if it's even, our point was outside, we don't draw it. We don't fill it, I should say. And then odd, the point is inside. Let's take a look. This one is even, right? In and out. 1, 2, 3. This one is odd, so we color it. 1, 2, even, we don't color it. So in this case here, I fill in this one, even. I don't fill in this one. Great. So this gets filled, and the other region here for the bottom line doesn't get filled. That's the even odd parity rule. There's a different rule which results in a different shading, and the other rule is called the non-zero winding rule. Okay, the non-zero winding rule. And what we do is we don't just look at how many crossings, we look at the direction of the line that we cross, the winding of the actual triangle, the polygon. So for each crossing that we find, so we do the same as the even odd parity rule, but instead of just counting them at each intersection, we check the cross product. We add 1 if the cross product is bigger than 0. We subtract 1 if the cross product is less than 0. Okay, so therefore our total, we will get 0 if the point is on the inside, and we'll get non-zero, the point is on the outside. I got that backwards. I'll go through. Don't worry. I'll go through some examples. We will get 0 if the point is on the outside. That's right. That's right. Yeah. There it goes again. We'll get 0 if the point is on the outside, and we'll get 0 if the point is non-zero if the point is on the inside. Now that I've thoroughly confused you with those two, let's look at this and figure out some example. So what the idea behind this rule here is, the non-zero winding rule. The idea here is we want to account for the fact that if something's going counter to our winding, it works in the opposite way. It's something gets canceled out. If it's in the same direction as our winding, it shouldn't be a hole. It's part of the filled polygon. Let's look at what happens here. So here, we start here, good. The first crossing goes right, then it goes right, so +1, +1, or -1, -1, and then it goes the other way, +1. So this is non-zero, because I get 2 in one direction, 1 in the other. This is non-zero, the point is on the inside, so just like the other one, it gets drawn. Up here, the winding goes left, then it goes right, so this is a 0. I should change it to red. This is a 0. The winding's a 0. Perfect. Then we don't draw it. Why is there a 0 here? Let's just try to make it look a little cleaner. This bottom one, I go right, and then I go left. This is a 0. Okay. This is a 0. So the point is on the outside. We don't draw it. Now, if I did this, however, wait a second. It's the same thing. Yeah. Whew, I confused myself. Yeah, I turn right, I turn left. This is a 0. So in this case, it does work out to be the same, but these two rules actually have distinctive properties. So let me show you a slide where you can see that. Slide 4. Instead of drawing another big example, I'm just going to show a slide. Oh, come on. There we go. So as you can see, oh, you can't see that, can you? Let's try that again. Here's an example here. In this region here, I'm not caring about the winding of the polygon. It's a non-even parity rule, so even odd parity rule. I cross 2, therefore I must be in the outside. I don't color this region here. Here, because the windings are both clockwise, they're considered to be the same side of the polygon, right? So even though it's an even crossing, they're both turning to the right. They're both -1s instead of +1s, so this gets shaded. So with the non-zero winding rule, these regions that are the same winding inside, they don't get canceled out. This would have to be wound in the opposite direction to get canceled out. So they are different, but very similar. So I'll have some notes about that. Okay, so if you hear something, it's my dog is running in his sleep again. He might have stopped now. So if you hear yelping, he's probably caught a rabbit or something. Okay, let's close this. Now I got distracted. There we go. So if we compare these two, even odd versus non-zero winding, even odd is simpler, but the non-zero winding tries to cover embedded regions. Same winding gets shaded. So that's what happens with those two. Now, I mentioned this for the triangles, but we can optimize this using edge tables. Right, we go through the lines once, we put them in the edge tables, we go left to right, we can count the crossings. There's a lot of ways to do that. I'm not really going to get into it because, like I said, shading polygons is slowly turning into an academic exercise in my opinion. I could be wrong, but it's not as important as knowing the other details, and those are things you can look up. There's a couple special cases I want to highlight. One is what happens if my arrow just hits a vertex, and the other is what happens if my point is coincident or collinear with an actual horizontal line. So the first one is if I hit a vertex, we still hit both lines, right? Because both lines have a point at the exact same spot. Great. Even though when you rasterize them, you might not do that. The actual point in formula form, they both cover the same point. They need to have the same endpoint. So it's still hit twice. So that's great. The other one is horizontal line. This is a special case you should check for. And you can determine if you're on a line with your cross product and you go, oh, I'm on a line, I draw it, or I'm on the line, I don't draw it, depending on the rule that you set up. The other way that you'll see this whole problem being solved is instead of casting my rays on the pixel point, what you can do is you can offset them by a half pixel. Let me just show you what I mean by this. So this is a line of my polygon. Imagine this. Okay, so the polygon's on one line, it goes up as an outcropping. When you cast your rays, instead of being coincident, you offset everything by a half pixel. So the two cases here you can see, I'm not hitting this horizontal line, so you won't have that crossing. Special case solved. And the vertex, I can never hit it because I'm offset by a half pixel. I still get those two crossings. So that's another way to do that. All right, so the last thing I want to talk about with polygons is that polygons can have holes. They can have holes on purpose. We've seen that already, but I want to really go into a little more detail on how that can work and show you how that might happen. So the first case is like this, where I could imagine I have a vector here, and then I go down to here, Now I'm going to go in the opposite winding just because I can. There we go. Let's fix that. Okay, so you can imagine this is a simple polygon and we have a hole, and I can go through these examples. Even, odd, I hit 1, 2, that's even. I'm outside, not filled for even, odd, but I didn't draw the windings on that one. That's that way. There we go. But down, down, this is not 0, so this is filled with winding rule. Okay, another example here. Let's see my windings. No, I did it this way, didn't I? Yeah, that's okay. Easy enough to fix. There we go. Okay. Same thing in here. Even, odd, and the winding are both not filled. So here, 2 crossings not filled. Turn left, turn right. Even the non-zero winding rule, it's not filled, so it's the same. So let's draw another case. You can imagine drawing a polygon that's actually in 2 segments. You can do this. Why not? And then I'm going to draw it with this winding. So here, even, odd, right? Drawn, not drawn, even, odd, and then the winding is in opposite directions, so it's also not drawn for the non-zero winding rule. However, the winding does matter, because if the center hole is wound in the same direction as the rest of the polygon, the non-zero winding rule would still fill that. And here's just an example of different results with the different algorithms. Okay, that's all we're really going to do with polygons. Like I said, the real solution with polygons is to triangulate them, turn them into triangles, tessellate them, get a triangle cover of that area, and then use the triangle algorithms. It's a bit more generic, but I still think it's useful to learn these algorithms to know how it works with polygons in general. Thanks.